Okay, since last Houston, we have some small problem here. So my name is Yuchen from Tsinghua University, and today I will present our paper DROW, and training-free load speculative execution attack on Apple Silicon. So in previous talk, a lot of work has shown that the control flow can be explored to conduct transit execution, and they may combine with another component to conduct a secret leakage. So today I will talk about the data relative speculative. First, we see the abstract model about the load store unit. We got a load address queue, and we got a store address queue and the store data queue. So to prevent unnecessary store, modern processor may deploy the prediction mechanism to prevent the store, such as they may predict load data, they may predict load address, and they may also predict load store dependency to conduct neither store to load forwarding or store bypass. So our new finding in Apple Silicon is that there was a very aggressive speculative policy has been deployed, that when previous store has been stored, and the following load will unconditional bypass previous store and load ahead of previous store. So when giving this gadget, we see here the line 2, we have a store with a store index, and the line 3, we have a load with another load index. So the value of the store index and the load index may be same, but when the store has been delayed, the second load will be speculative conduct and bypass the previous store. So when the index was sent, the CPU will check that the previous load was violent, so it will flush the pipeline and reconduct the load. So here is our a kind of new type of the spectral attack. So compared with previous work on load relative speculative, they require for slab or flop, they require hundreds of training to making the predictor learn the value they want to predict. And even for previous work, such as store to load or cache to load, they still require dozens of training. But for this type of attack on Apple Silicon, there is no training requirement to making this speculative happen. So what is the value? We know that we can see that there was a lot of training overhead. So a lot of mechanism has been deployed to defense by prevent the training. Well, the training-free attack can bypass this mitigation. So let's see a typical attack flow. So the attacker needs to train the predictor at the attacker domain. And then as most of the predictor will share across different security domain, the victim may using the state that interact by the attacker to conduct a speculative asset and leak the secret. So there are 3 types of major mitigation to prevent this kind of attack. So first thing is flushing the history, such as Intel IBPB. When context switch, the system may flush the state of the predictor. And the second is domain isolation. Some kind of the predictor may add the contents relative tag to prevent the entry to be shared. And the third is adding the complexity for the training, such as add a noise to the prediction when context switch, or randomize the predictor between different security domains. So for the data relative speculative, the attacker needs to prepare a store load pair that will have stored and load with different address. So in previous work, there will exist a predictor that learned that the store pair are irrelevant. So when they need to conduct the final attack, they prepare a send address to be stored and load. So when there comes a speculative, the further load may speculative execution before the store, and using the store value to conduct a load, and finally transmit the secret via a traditional flash reload convert channel. But in Apple Silicon, with our spectral blind bypassing, there is no need for training. We just need to store the store. So this attack can be more simple, and we can also bypass the training relative mitigation. And there will be less noise and without a training overhead. So you will have higher bandwidth. We also test this mechanism's deployment about many chips, such as from M1 to M4. We can see here, even we increase the iteration of attack, the load will always to speculative load a store value before have been override by previous store. And on another ARM chips, such as Cortex-76, it will not have this aggressive speculative. So we also take research about different operation dependency. Most of them will active this blind bypassing mechanism. And to conduct a real-world attack on Apple Silicon, we're facing another challenge that we do not have CLFLASH instruction, and the DC-CIVC instruction is inaccessible into user space, and we also cannot configure the PMU for M4 chips. So we develop another mechanism, is called cache coherence. So when the attacker prepare a worker thread on another core, when the worker thread write to a shared memory, due to the coherence state, the shared memory on another core's L1 cache will be invalidation. So it will create an effect such like a flash instruction. And this mechanism can also be explored on browser environment to conduct a web spectre. So our real-world exploitation is cross-website leakage on Chrome. As we know that the random process in some of the scenario, different website may share something in the random. So if we can trigger a speculative with out-of-bound index to conduct a memory access, another website's value can be leakage and transmit via a flash reloc like convert channel. So we are able to leakage the secret from one website to another website. And we have also tried to use this speculative mechanism to break ASLR and the KSLR. Here is the scanning result, and the pack mechanism, pointer authentication, can also be break by testing which pointer can leave the side effect on the cache channel. And to be conclusion, we find a new attack variant that it was the first training-free speculative primitive on Apple Silicon. We're able to achieve high-gain attack bandwidth and conduct different real-world exploitation, such as website leakage, and ASLR, KSLR breaking, and pack breaking. And the next step we will research is to search the real-world exploitation gadget to conduct a real-world, more serious attack. That's all. Thank you.
Perfect. We have time for one question. Okay, Mate. Wait.
How did you find the Spectre gadget or the store-to-load forwarding gadget in Safari?
Okay, there are two kinds of scenarios. For website scenario, we assume that the victim may access attacker's website. So at this scenario, the gadget can be read by neither the WebAssembly or the JavaScript. And it was easy, such as this kind of code pattern. And for another scenario, such as kernel and crypto laboratory, we need to using the kind of mechanism such as symbol execution. We prepare a register state, and we using this state to execute some kind of kernel code and see whether the different store load pair will using the same address. So if that same address has been checked and the register are different, so we consider this is maybe a potential real usable gadget. Okay, I hope I answer your question.
Yeah, we have no more time for questions, but thank you so much. One more thanks.